Hello, I'm Torben Logemann from Karl-Ossietzky University of Oldenburg from the research group Adversarial Resilience Learning. My research interest is explainable deep reinforcement learning for agents in Power Grid. In our research group, we are going to build the DRL framework for the use in Power Grid. We'll take the agent application in critical nation infrastructure onto the next level. We will include discrimination between adaptive and user input, rule-based policies, continual as well as on and offline learning, explainable deep reinforcement learning, and neuroevolution of policy models. Now I'm going to present the NN2EQCDT algorithm that does an equivalent transformation of the feed-forward neural networks as DRL policies into compressed decision trees. First of all, I present some reinforcement learning basics. On the right, you can see the basic RL control loop. There's an environment that has time-dependent states. An agent observes these states input and compute actions as an output. The actions are played to the environment, in which the critic evaluates their impact according to a given goal and returns reward to the agent. The agent may be some simple controller, but can also learn deep neural networks through trial and error using different algorithms. This combination of reinforcement learning and deep neural networks is called DRL, deep reinforcement learning, and have proven that it is capable of handling complex tasks. There are some popular DRL algorithms with success of end-to-end learning of a Terry game in 2013 and double Q learning as a major breakthrough. Further successes are AlphaGo, AlphaGo Zero, AlphaZero, and Mu0. Common algorithms are DDPG, which we also use for training simple models, PBO and SAC. Besides policy-based RL, there are also Q-value-based algorithms, which was the first ones. Reinforcement learning is applied in various fields. In healthcare, reinforcement learning is used to determine the best treatment policy. It is now even preferred over traditional simple DNN-based methods. In robotics, for example, reinforcement learning agents can learn different tasks to reach higher goals, such as pouring water, reaching goals through a human teacher, grasping and balancing balls, and more. DRL is used in autonomous driving because of its strong interaction with the environment. And in cybersecurity, DRL is used for automatic intrusion detection techniques and defense strategies. In our domain, in Power Grid, DRL is, for example, used for voltage stabilization. We used it, for example, to train an RL defender agent to recover from deviations from the healthy state. To let the defender be faced with various situations, also an RL attacker agent is deployed in an auto-curriculum setting. Next, I motivate why DRL agents have to be explained. On the one hand, DRL learn agents promise true resilience by learning to counter the unknown unknowns, which is needed to increase the safety of critical applications. On the other hand, the observed behavior cannot be guaranteed yet to behave as wanted. One issue is that DRL may be used to train black box DNN models that are not interpretable and unlike other models like decision trees. But it is a necessity for operators to have controllers with guarantees to handle the risk. Otherwise, no responsibility for a control system with unknown behaviors can be taken, especially in critical or very critical applications such as CNIs, because the controllers have the potential to significantly threaten the safety of the overall system. For critical applications, we already presented an architecture that have the potential to provide such guarantees. Next, I will describe how agents' achievement classically analyzed, and we did it in an example. In complex environments such as complex interconnected systems, agents potentially face many different situations and learn complex behaviors to cope with them according to the goals. The current state for understanding the complex behaviors is to study the effect of their strategies in terms of rewards or impact on the environment. In one scenario, we deployed RL attack agents with the goal of causing voltage band violations in the power grid. They achieved this goal by exploiting a vulnerability in the deployment of the voltage controllers in the used network. We analyzed this by visual inspection of the impact of attacker actions on victim buses. The problem with that is that there is no deep interpretation and no guarantees for all situations, because not all situations can be extracted with this visual analysis. But an explanation and also actually a validation, which would be a further step, is crucial for example, with defender agents with an infinite horizon that may face rare situations, because a defender also have to achieve its goals in such situations. So the goal for the guarantees is to first explain the learned strategies of agents. The first idea, one could use decision trees for explanation because they are transparent and therefore interpretable. They also could be trained directly, so there would be no need for black box DNN models. But we don't train them directly because DNNs are better regularized, which increases trainability, and the DRL algorithms are constructed for DNN models. A high trainability is particularly relevant when sampling efficiency is required, as in the training of DRL models, where there may be long trajectories that need to be calculated by computation-intensive simulations. So there are the conflicting goals of the construction of powerful DRL learning systems and the post-hoc explainability of the comprehensible models such as decision trees. Our contribution to this problem is the NN2EQCDT algorithm that does an equivalent transformation of efficient, learnable, feed-forward deep neural networks into compressed decision trees. It aims to extract an exact understanding, and not an approximative, of the hidden knowledge in learned DNN models instead of approximation that comes with uncertainty. The restriction to simple feed-forward deep neural networks is sufficient for proof of concept in general, and actual for some applications, because the DNNs may not be that large and that complex in its architecture. The NN2EQCDT algorithm heavily relies on the equivalence description of deep neural networks and decision trees from ITKIN. But there are still addressed research gaps to better use it for explainability. We provide a transformation algorithm and actual implementation for the right-handed linear transformation of standard PyTorch models. The exponential growth is addressed by lossless compression and the dynamic compression that significantly reduces computation time and may reduce inference time. There is also the option to directly include invariants like input sensor domain constraints for further compression. As you can see here, this is an example for PyTorch sequential model with linear and ReLU layers that can be trained and used as an input for the NN2EQCDT algorithm. This is actually used in the simple example with the hidden size of 8 later on. This is the pseudocode for the algorithm itself. First, there are some initial values and constructed an initial subtree. Subtrees are generated layer-wise from weight and bias matrices, to which different activation matrices are applied. These are denoted by the A vector. They are activation specific and are connected to the leaf of the higher subtree with matching the activation path. When adding a node, the path with the check of the current node is dynamically checked for satisfiability. If it is unsatisfiable, like x is greater than 0 and minus x is greater than 0, if you have these two constraints, the node becomes an unset node, which indicates that no further nodes and therefore walled subtrees are added upon the unsatisfiable path. Lastly, the tree is further compressed by removing unset and also its parent nodes. We will show it in a later slide, as well as replacing the parent node position with a satisfiable subtree. This is the analogous algorithm that is also used in the NN2EQCDT algorithm implicitly from the one ITKIN provided, that shows effective weight matrices calculation with right-handed linear transformation and bias for ReLU activation function. Here you can explicitly see the branching and activation vector construction. Next, we have an example construction for an XOR model. Here you can see the effective weight matrix calculation for the specific decision tree path and therefore activation vectors. This decision tree can be compressed by removing the unset and its parent node and directly connecting the third leaf to the root node, as you can see in this compression example. Furthermore, we learned a DRL model for the benchmark continuous mountain car setting and applied the NN2EQCDT algorithm to it. The model is capable to move the car upon the hill, as you can see in this GIF. This is the decision tree for the model. I'm sorry that it is so fast, but you can also have a look at it in the referenced repo in GitLab. We also focused on the 2D input and 1D output to be able to plot the splitted sensor regions to the output actions. This you can see in this GIF. Plotted this with Plotly, and you can clearly see the two regions where the actions climb this hill in this landscape to reach the high position that is correlated but not exactly the same as the Y position in the hill climbing of the mountain car. The decision tree of the equivalence description can be calculated by this formula. Here you can also see that it grows exponentially with the 2 to the power of I term. For this simple example, we did not measure the actual computation time because it took longer as 1.5 hours, and we only wanted to show that the NN2EQCDT algorithm is significantly faster with only 10 seconds and create a small decision tree with only 83 nodes in comparison to the calculated over 260,000 nodes without compression. This leads to the compression ratio of overall 99.97% in terms of the amount of nodes. Because we cannot say it in terms of computation time, and also not in general, there would be more benchmarking of this algorithm needed. To conclude, we can say that the algorithm equivalently transforms feed-forward deep neural networks into significantly and lossless compressed decision tree for better explainability of learned deep neural networks as DRL policies. We provide also the transformation algorithm and actual implementation for the standard PyTorch models as input, and we have evaluated it for a simple model. Thereby we observed a high compression ratio, and it seems to be a good trade-off between the powerful and efficient learnable DRL models and the explainability of learned strategies. These are the references used for this presentation. And then thank you for your attention.